All right. So my name is Jasmine Blewett, and today I'm going to be talking about BCI exoskeletons, specifically towards a full body application for ALS. So what is a BCI? A BCI is a brain-computer interface, a computer-based system that acquires brain signals and carries out a desired sequence of actions. It acquires these signals through sensing technologies and uses usually machine learning for feature extraction, translates those features into motor intentions and executes them through some type of motor towards controlling an exoskeleton. The main goal of BCI is to replace or restore useful function to people disabled by neuromuscular disorders such as amyotrophic lateral sclerosis, cerebral palsy, stroke, or spinal cord injury. This really indicates how beneficial BCI is to patients with neurodegenerative diseases in which other processes like EMG might not be as effective. So, one of the best ways to accomplish this is by electrocorticography, ECOG. It's a very high signal to noise ratio sensor that does a really amazing job of collecting the brain signals that we're looking for with a BCI. However, the typical methodology for this requires a very invasive craniotomy that is often not medically defensible for its applications. One of the research studies that has looked towards reducing the invasiveness of this procedure is this one by Coles et al. They propose, excuse me for a second, they propose this flexible inflatable array. So it starts out here at this 5 millimeter compressed state. It's able to be inserted through a 12 millimeter hole called a burr hole in the skull, and then inflated within the brain and placed on the cortical surface, allowing a far less disruption of the kind of physical structures that are there, and that is expected to reduce the complication factors and the recovery time for such a procedure. This study was done in pigs, live pigs, and so it's not quite yet ready for human application, but it does show some really good hope towards being a future where ECOG might be applicable. In addition, the work of Rochford et al. Demonstrates a methodology for creating biohybrid sensors, which is essentially a sensor that has stem cells around it, allowing it to fuse with the existing neuronal tissue and allow for biological signal amplification, basically meaning that it integrates fully into the existing structures and has less of the issues of a normal sensor, including that there's typically better healing with that. Once again, this wasn't a human application, this was done in mice, and so we're not quite to the point of applying this into a practical system just yet. But there, per a quote from Rochford et al., biohybrid neural interfaces could be adapted through the use of different transplanted cell types, such as those with neuronal or glial phenotypes, to promote integration with other tissues such as brain and spinal cord. So her study was not on cortical material. It was, I believe, at like a lower, more spinal level, but the technology and the processes she used would most likely work for other types of cells in neuronal processes. So it would most likely work for an ECOG. So, what can we do now? EEG sensors are way cheaper. They are way lower signal to noise ratio, so they're not quite as quality of signals, but they are also generally not implanted, so they are able to be applied to multiple participants. and they are a lot less costly because of not having to implant them and do surgeries, excuse me, and ensure that those surgeries are going to be safe. So the work of Yang et al. Proposes the use of a higher effort SEMG signal, so a signal from residual muscle activation, in combination with the lower fidelity EEG signals. And the reason for this is because the SEMG signals tire out the patients pretty quickly. And so using the EEG signals allows for continued control of a system after the patient has already grown tired. This is also a application that was able to be really, really low cost, and you can kind of see the photos here, which is a very big area of benefit for this, since many of the exoskeletons can end up being quite expensive. The work of Rodriguez et al. Was very surprising to me and very interesting in that it used EEG to determine emotional state in nonverbal users of a gait exo in order to get feedback that they couldn't give verbally on how well their therapies were going. And this is really interesting for further applications because it was in real time, which means that you can get real time measurement and data on the emotions of users while controlling an exoskeleton, which might be useful for evaluating more quantitatively satisfaction and things like that. So, control. A lot of BCI exoskeletons are controlled via machine learning algorithms rather than physics based models because they are able to be more personalized and accurate to the kind of complex motions that will be involved here. One big cost of this is that they are very computationally heavy, and that can be an issue for real time control. However, Sarasola Sands was able to accomplish a smooth, continuous, real time control of a 7 DOF exoskeleton with both EEG and EMG signals via a hybrid brain muscle machine interface. One of the things that they did that I thought was really interesting was the use of a linear quadratic regulator and optimal control tool. And they used this essentially to minimize their fudge factor gain. Essentially, they put in a gain to account for system imperfections like friction and low participant signal quality, which was causing the participants to get really frustrated because the BCI wasn't doing quite what it was supposed to be doing. And so they were able to account for some of this by adding the LQR, but they wanted it to still encourage the user to send signals well. And so that's why it's minimized. So, rehabilitation, the whole point of everything we're doing. One of the key ways that rehabilitation assesses effectiveness is the Fogelmeyer test. It's a common rehabilitation test in which clinicians essentially watch a patient perform an action and rate how well they performed the action, with higher scores being better. So, Takasaki et al. Used a scalp EEG to help reestablish and reinforce remaining neural pathways after a stroke. And they were able to demonstrate really promising results in the Fogelmeyer performance of their patients without their shoulder exo. So it worked really great when they were wearing it, but it actually improved their ability to do it on their own as well. Zhao et al. Was really cool in that it was able to use a intercortical array, a much more invasive procedure, just by the way, to control a Ford Mustang through a essentially simulated city, but like a course similar to what you would see when people are being trained to drive as like teenagers. And they accomplished this using a hand-based system. And so that was really, really cool. And what brought me to this was this Brainstream podcast that followed a patient experience of a very similar study, and it really emphasized how empowering this was for his autonomy and how valuable that was for him psychologically. So, why do we need a full body exoskeleton for ALS? So, amyotrophic lateral sclerosis is a rapid progressive neurodegenerative disease characterized by the degeneration of both upper and lower motor neurons, leading to motor and extramotor symptoms, with death usually occurring 3 to 5 years after the onset of symptoms. So, time is very valuable for participants with ALS. They don't get a lot of it. And so it's very important to help them have as much autonomy as they can during the time that they have and be able to do all of the things that they want to do. So, this study by Trad et al. Showed really promising results for the patient experience, safety, and functional capacity with lower limb exoskeleton usage for slow progression ALS in a lab setting. What they found was that exercise in patients with ALS can significantly improve functional ability and pulmonary function and may help slow the development of muscle weakness, thus facilitating their performance in ADL. So, from this, essentially, being able to engage in exercise through the use of an exoskeleton may actually be helping to reduce the effects of their disease short term. It unfortunately does not seem that it is going to completely cure the disease, but it may help slow the progression and give these people back some much needed time. So, to expand on the amazing work that they did, this proposal theorizes that a deep learning based full body BCI exoskeleton designed to adapt to increasing user need over progression of ALS will enable continuation of ADLs, increasing life satisfaction. So, how are we going to do that? The first step is the development, and this is for sure the hard part. So the ideal situation is going to be to inter-integrate existing BCI devices and existing exoskeleton devices. There are a lot of devices on the market that control, the arm and the leg and the hand all separately. But the primary goal of this study is to create a system that will accomplish all of the functions that are needed for someone with full body paralysis. And so finding a good way to integrate all of those systems so that they can be controlled together well will be a bit of a challenge. If this can't be accomplished feasibly or economically, the kind of second resort is going to be to design those from scratch. And then, of course, the selection of appropriate EEG arrays and components will be crucial to that stage as well. The design of the study is intended to have 16 to 20 participants divided into 4 categories: control, early stage, middle, and late stage ALS. And having this number of participants is really important for the generalizability of this data to multiple populations and for showing that it works for more than just one person. Hence the selection of an EEG, because it provides the wonderful safety and defensibility criteria that we see with an EEG, but it also allows us to apply it to multiple participants economically. The second stage is going to be training the deep learning model on the initial cortical data from these participants, most likely through a resting state measurement and a light activation measurement. So, like lifting like 2 pounds or something, just to help differentiate motor intention versus intention to stay still, with kind of an iterative process to that of what data is needed to get the system fully functioning. The third is to verify through a series of resistance exercises that are very controlled to ensure that it is assisting when and only when it is needed. So if we know that the participant can lift 10 pounds on their own, we might have them lift 5 pounds and see whether the device is picking up that 5 pounds alone or whether it's trying to pick up the full 10 pounds. So ensuring that it is doing what it's supposed to be doing fully and safely. And then the fourth kind of stage is to have participants engage in ADLs or something similar to what their ADLs would be in either a true or closely simulated normal environment, with true environment being the preferred solution. But if there are safety concerns around performing things in a normal environment, which might contain, bystanders, then it would be a closed lab environment to account for that. So some potential concerns with this study is the computational heaviness of deep learning, especially since for effectiveness, this study needs to be real time and full body. There's a lot of load at very necessarily fast rates that will have to be accomplished for this. And so it will be very important in the development of what systems we're running this on, and the way in which things are coded will completely determine the success or failure of that aspect. The physical implementation is going to require very good motors that are high torque, lightweight, as well as really good high power batteries that also don't add a lot of weight. And so these two things will probably end up being cost drivers. It's also going to require a lot of medical expertise just to make sure that this study is benefiting the patients and is not putting them in any kind of jeopardy. Another big concern is the insurance is not typically great about covering the cost of ALS centers. And that could prove to be a potential roadblock to the financing of this study, as well as the financing of this as a future available product and who all might end up having access to it. And so it's important to ensure that there's a good path to this being generally applicable. Another consideration is that, especially for late stage patients, it may be difficult to convince them that this is a worthy use of their limited time. And so it's very important that there's a good case for how beneficial this will be for everyone and hopefully for them. But since it isn't a direct cure that may be able to help them the most directly, that will be a consideration. One of the other big concerns is informed consent in a neurodegenerating population. This may require a hybrid structure of family given consent as well as participant given consent, both of which would be retractable at any time. And really, I would say the biggest concern is that although the hope of this study is that increased autonomy in this population will increase their psychological mental health and will bring them more life satisfaction, there's a possibility that increased autonomy in a terminal population may actually end up posing risks of self-harm, which will need to be managed through initial screenings as well as continuous screenings and very robust psychological support for the patients in this study. So, how are we defining success for this study? The primary goals being that the controller is actually performing the desired commands as intended. This will be kind of measured by the percentage of time in which it is actually executing correct commands. And then the accuracy with which the controller is gauging and executing the adaptive assistance component. So whether it misguesses what amount of assistance it needs to provide. Users will also be given a expectation and a satisfaction survey as a pre and post survey to this study, which will be anonymized, but will be correlated by an ID number so that the initial expectations can be correlated to the final results to essentially eliminate some biases. In addition, for the generalizability of this study, the participants will undergo a full Fugl-Meyer assessment, both wearing the device and not wearing the device. So to wrap up, this study contributed a especially significant amount to the field because its applications to ALS are pretty underexplored. There's not as many studies in this area that I was able to find. And also because there are very few fully integrated holistic systems that have been developed for BCI exoskeletons. So, just to recap what we talked about, we discussed key sensor options and advances, controls and rehabilitation, and a full body application in ALS. BCI exoskeletons are an incredibly interesting and quickly progressing area, and I'm so excited to see what this area is able to produce. Thank you so much. And just FYI, these are my references. I have no idea how long that was.